Good afternoon, dear student. Welcome to this other edition, the 7th of our functional analysis class. So we are done with the recall or the overview of Lebesgue measure and Lebesgue integration, which we also call generally as measure and integration theory. Now we will go back to the rest of, to the normal progression of our module. So we are going to talk about metric spaces. You know already what is a linear space from linear algebra, so I'm not going to detail, and I hope you have time to read and go through. So it will be a waste of time at this stage if I have to spend some time again. All these subspaces were covered in linear algebra course. What is the basis and all that? This is just revision, so I will not spend time there. Okay, maybe what you might not know that much is about equivalent relation. But you can still read here because the definition is given here. When is a relation reflexive, symmetric, transitive? So when a relation satisfies this precondition, we say that it's an equivalence relation. And once we have an equivalent relation, we can always define what we call a factor space. And this is an example. So you have some example here, the factor space here. And if you recall, when we talked about the capital LP space, we said that the capital LP space capital like this. Of course, we assume that it's of a certain omega, where omega is the domain of Rn. Or I can just keep X here. So we say that by definition, what is it? It's a factor space, right? It is this LP of X by this equivalent relation. I think this is what we call the mu, right? We have a measure of mu here. And this relation, F is in relation with G if and only if F is equal to G mu almost everywhere. So that was our relation. It's an equivalent relation. So if we take this factor space, that's what we call capital L, the LP space. So it's exactly the same way. So here you have a space, and this is a factor space where R sub n is an equivalent relation. And you can see here through this example, you have an example of what is a factor space. All right. So this is an example. You can go through. I hope you did it. Okay. Topology through open sets. We also covered that in one of the previous videos when we were talking about Borel, sigma algebra. So we went through this and we saw how we can define, you can identify that a space or a family of software space is not a topology to open sets. So we identify some cases here. Okay. Construction of a topology. If you remember with X X2, X3, sorry, X3. We saw previously here that X3, this one was not a topology in X to open sets. But we can use this to construct, right? So for an arbitrary family of subset of a set X in this case, the underlying set, if you have an arbitrary family of subset of X, which is not a topology in X2 open set, we can always construct from that one. And this construction is simple. This gives us the algorithm or the steps to reach that goal. So the first thing is to check if the empty set and the underlying set are there. If they are not, we add them, like in this case, or in our X, the empty set and X are already there, so no need to add. But if they are not, you add. And then we make sure that all finite intersection of element of the family is in the family. Like in this case, we realize that the intersection of these two, which is beta, was not there. So we take the intersection with it, we add. So we check all finite intersection. So if we get a new set which is not there, we add. So we make sure that all finite intersection are there. Right, that's finite. And then arbitrary union, all union here, all arbitrary union are there. So we take all possible union that we can imagine from element of the set or of the family. We just add. So at the end, we will obtain a topology through open sets. So this is an example. I encourage you to go through. So if you recall, we know that the pair empty set and X, the underlying set, is a topology, and that's called the trivial topology. And the topology made of Px, that is the power set of X, is what we call the discrete topology. Discrete topology, yeah. So for any topology X on T on X, the discrete, the trivial topology will be contained, because we know that all topology will always contain the empty set on X. So meaning that it will contain the trivial topology, and they will all be contained in the discrete topology. Because we know that when we define a topology, all the family, a topology which is a family of subset of a set, the underlying set X, is a subset of Px. So that is from the definition you can see here, given a non-empty set X, a family that is a subset of the power set. So it is always a subset there. So for any topology, that topology will be sandwiched between the trivial topology and the discrete topology. And that's exactly what we have here. So that's a good remark. Okay, if you remember what we did with sigma algebra, we saw that if you have a sigma algebra, the intersection of sigma algebra is a sigma algebra, and from there we define what we call sigma algebra generated by something. In a like manner, if we have a family of topology on X, we can always define the intersection of the family. So we take the intersection of all the elements of the family of topology. It's still a topology on X. And similarly, we can define the generated topology, or the topology generated by a set or a subset or a family. Like in the corollary here, if we take calligraphic A to be a subset of P, which necessarily is not necessarily topology, it's just an arbitrary family of element of family of subset of X, that is a subset of the power set. And we can construct the topology generated that is the intersection of all topology that contain that A, right? And that will be the topology generated by A. Exactly what we did with sigma algebra, so we can also construct that. Okay, so we have a definition here. If you take A, a subset of Ex, the power set of X, and A, a fixed subset of X, then the family A sub A defined as follows, that is A calligraphic A sub A, which will be the intersection of any element of A with A. This is called the trace of A on the set A. Okay, so the following proposition gives us this result. T is a topological space on X, and A is a fixed set, a subset of X. Then the trace of that topology on A, denoted T sub A, is a topology on A. That is the induced topology. It's called the induced topology. And we know what this TA is from the above. We have already an idea of the structure, right? Because our T is like our calligraphic A here in the definition, but beside it is a topology. So TA here will be defined as the element of TA will be the intersection between the element of T and A. Simply like that. Okay, so if you look at that example, so we take this set that is open at 0 and close at A. So we have that interval 0, 1. Interval open at 0, close at 1. This is a subset of R. Obviously, if we consider the topology of R, this set is neither open nor closed. Now, if we define the new topology, which is the induced topology, because this example is the follow-up of this proposition, is to exemplify the proposition. Now, if we define A to be the closed interval -1, 1, close at -1, close at 1, right? Take that. And then we define the induced topology, on A. So if you define the induced topology on A, then the semi-interval, that is when semi-open, semi-closed, this interval 0, 1, open at 0, close at 1, becomes open for this induced topology. Open for the induced topology. Okay, now, what is an open set for a topology? We know that an open set for a topology is an element of the topology. That is, here we define our TA for this case, TA. So any element of TA will be called open. So is this an element of that? Let's look at that and see. Okay, so by definition, we know that this will be set of what? B intersection A, right? Where B is an element of the topology C, right? So now what is our topology here? That is the usual topology of R. So T here is this one is TR if you want. TR, the usual topology of R. So this T is the topology of R. Obviously, I would like to write R here. that it should not hurt anybody, right? Okay, let me do this. Good. Okay. Now, to know if this is an element that is open at 0, close at 1, is it an element of TA? In other words, can we write this as the intersection of an element of TR that is open set, because we know that the topology of R is a topology generated by open sets, right? So an element is in the topology of R if it's an open set, and we know how to write an open set in R, right? It can be arbitrary union. An element there can be, because we know the definition of a topology, it can be either an open set, that is open interval, open at both ends, A, B, open at A, open at B. And we know that an element of the topology can also be any set that can be written as an arbitrary union of open set. That's also an element of the topology, or it can be written as finite intersection of open set. If that's the case, we are done. But it turns out, right, if you take that interval, we can use, you can just use our interval. You can take an arbitrary interval, provided, right, we know already that any open interval, so because I want that, I can take this open interval 0. I can even take the interval 0, 1. But if I take 1, it will not be good, but I can take 1, 2, for instance, comma 2, like this. Then I take that intersection with A, and what is A? Negative 1, 1. Negative 1, 1. Okay. Now, if you want to look at the common point to the two interval, you do exactly what you did in first year in set algebra and trigonometry. When you draw the number line, you want to look at the intersection, right? If you take this and this, here you have, this is, let's say that this is negative 1, and this is 1. Here we have 0, that same 0 is here. Now, if you want the open interval from there, you can do this, open at 0, up to 2, 2 is somewhere here. Okay, so this is 1, and this is 2. So this is 2. 2 is here. Okay, so let's see, this is 2. So this is 0 here, and this is 2 there. Now, if you want to take the intersection to both, that is negative 1, 1, and then 0, 2, the intersection will be this one. Right? The common to the 2 will be from 0. So you see, already is open at 0 here, and it is closed at 1. So it will be this. So it will be 0, 1. So this intersection will give us 0, 1. So yes, but because it can be expressed this way, we say it is open for this topology, the induced topology. So to conclude, there is something you need to bear in mind all the time when you talk about topology. So topology is a relative expression. So when you say that a set is open or it is closed, it is relative to a topology. You don't just say open is an open set. For which topology? So when you say that something is open, you have to indicate with respect to which topology is it open. If you say it's closed, with respect to which topology. Because if you say to somebody that this is an open set, he will look at you. With respect to the usual topology, it is not. But if it's with respect to the induced topology, right? Induced topology on A. And our A here is -1, 1. So if we take the usual topology and we induce it on the interval, that is, you take that topology, you induce it, so that you take all open sets, you take the intersection with A. Because when you talk about something that is induced, you restrict. You take something that exists, you restrict it to something smaller. You talk about induced topology, induce whatsoever. Something that exists can induce something new. So to talk about induce something like induce topology, you first have to have a topology, and then you can restrict it in a smaller space or set. Then it becomes the induced topology. So if you take the usual topology, which is defined by open sets, and then you induce it, that you restrict it, you take intersection with, like here you have the topology of R, right, where the elements are the B's, you take intersection with A, then you are inducing that topology on A. Okay, so good. I think this example is clear enough. So we move to the next case. I will delete this. The product topology, right? I can really even skip all this, right? I will not go that far. You have the note you can read. You did something similar in real analysis, but with the topology of R. The reason why I designed the course like this was because previously, the first time when I designed this, these various aspects were not covered in real analysis. So that's why I designed the course then. Okay, but they are still valuable. It's still a valuable piece of information. For those of you who never did, and surely you will never do that again, general topology, which is really good for you to know, because for the future, you need to know these things. All right, but what I did here is just a generalization, right, of what you did in real analysis. Or if you did not do it, read it to have an idea. So I will not spend too much time there. It's just like an overview. I will talk about other more important aspects that you did not cover in real analysis, like what is a compact set. Things like limit point, contact point, accumulation point, closure, the like, you did that in real analysis. I will not stress on that. I will skip that part, but if you're interested, you can still read it. Okay, so let me quickly talk about the neighborhood. Okay, product topology. Okay, product topology. So if you have two topological spaces, meaning that you already have a topology on X, you have another topology on Y, you want to define the product or the product topology of X and Y. So the on product topology on the Cartesian product of X and Y, which is denoted by the tensor product like this, T sub X, tensor product with T sub Y, right? It gives rise to the new T, which is our product topology on the Cartesian product X and Y. So now, to define the topology, we need to define open sets, right? Because if you know the structure of open set of a topology, you know the topology. Because from that, you can build others by taking finite intersection, arbitrary union, things like that, and then you'll be able. Okay, now, I have already two topology, Tx, Ty. How do I construct the new topology, the product topology? Okay, so, so the topology, the opens, yeah, this open sets of that topology, that is O here, is said to be open. You can see now here, open, if this one, this O is not an element. I think this, not that I think that this is a typo. It should be a subset, not an element, right? So this is O subset, not element. Please correct that on your slide. So it is O subset like this. Okay, so this is a subset, that is a subspace. So no space, a subset, yes, a subset, a subset of the Cartesian product X and Y is open if and only if it is a neighborhood of any of its points. This is how we are defining an open set, a neighborhood of any of its points. So if you look at how it is defined here and the general definition of a neighborhood, we see that they are equivalent, right? Okay, so if for any xy in O, you can see that an element of O is a couple, because O is a subset of the Cartesian product, right? We can find an open set in X, that is Tx, an element of Tx, and an open set in Ty, such that U, right, the open set of Tx, contain X, and V, the open set of Ty, contain Y, and the Cartesian product of the two, that is the Cartesian product of U and V, is contained in O. In other words, O is open set if and only if it's the neighborhood of any of its points. So if I take a point in O, it will contain product of two open sets, each one, of course, being an open set containing the point X and Y. That is it. So that's how you define the topology, the product topology. Okay, now neighborhood, another way. You can see that now in this definition, this is a general definition, and it does not take into account the structure of the topology. Like, for instance, it doesn't say that your open set here is an open interval. No, it doesn't say that. You just say open. Open can be anything relative to the topology that you define. Just take open set, but it doesn't tell you if it's open interval whatsoever. And don't forget, from the previous example, not the previous, one of the previous example, when you introduce topology here, you see that we say that this is a topology. So the singleton alpha is an open set. So you see that just that for that topology is an open set. So when you say open set, it's relative to the space in which you are working, or the set and the structure of the set. So something that for you is a point or is a singleton, like in R, a singleton cannot be an open set. But here, for this particular case, you can see that the singleton alpha is an open set. So it depends. So that's why I say topology is a relative notion, right? Okay. So I was talking about neighborhood or all these definitions. We are just taking a general definition. That does not take into account the specificity or the structure of the underlying topology, just general topology, arbitrary topology. So what we are saying here is true for the x1, x2, x3 defined there, for those who are topology, like in this case. We can define a neighborhood of this, of the singleton alpha, and define its neighborhood using the definition, this definition. So this definition is general, and it holds for any topology. Okay, so a set V is called neighborhood of X, X being an element of capital X, which is the underlying set, as you can see here. X, an element of capital X, right? which is in a topological space. Okay, so V is a neighborhood of X if there exists an open set O such that X is in O and O is contained in V. In other words, to say that I am neighborhood of a point, I have to contain an open set containing the point. I am a neighborhood of X, so I contain an open set containing X. I'm a neighborhood. If I am already an open set, me the neighbor or the neighborhood of X, if X is an element, if I contain X, I'm a neighborhood of X. That is it, because I contain myself and I am an open set containing X, so I'm a neighborhood of X. So you can see that this inclusion is not a strict inclusion. So this V can be O. If V is O, like in this case, O itself is a neighborhood of X, right? So any open set is a neighborhood of any of its elements. But the definition of neighborhood goes beyond, because you can't be a neighborhood without being open set, right? Okay, that's good. Okay, so the set of all neighborhoods of X is denoted by Vx. Okay, contact point, limit point, I will not define that. You already know from real analysis, but it was defined in terms of the neighborhood of R, with the topology of R, which are open interval. That's how we define them. But here is more general, and this is a more general definition. So I will not go into all those restrictions. And you have other definitions here, right? Okay, so in the second tutorial that I uploaded a while ago, you have these. Of course, you did this in the topology of R, that is using open sets, right? But now in this particular theorem, you have similar result, but where T is an arbitrary topology on X. So you have the same result. I encourage you to try to prove it in terms of neighborhood. So these are the definition you'll be using. What is an open set, what is a neighbor, and so forth. So these are the information you'll be using. Like this proposition. A subset of a topological space is closed if and only if it is equal to its closure. So you can prove it using this definition here. Right? You know what is a closed set? A closed set is the complement of an open set. that one is what you know also from real analysis. If you don't know, I've just given you the definition here. Yeah. You know what is a limit point? This is the definition of a limit point in terms of neighbors, right? And the closure is the union of the set with this contact or the limit point. So that's the closure. Okay, so you also have the definition of something being dense, right? Like here, A and B, two subset of a topological space, XT, with A being a subset of B. So A is said to be dense in B. That is, you can only be dense in a larger set. Now we know that Q, the set of rational numbers, is dense in R for the topology of R, of course. In other words, the closure of Q is equal to R. So that's exactly what we have here. The closure of Q contains R, right? But since it contains, but it's equal, right? In our case, this is still correct. You can say equal or you can say contain. Okay, here it's contained, but if you look at the next one here, if you look at the next one compared to that one, that is now with respect to the topological space itself, dense in the topological space, not in the lower space, right? Okay, so let A be a subset of this topological space. A is said to be dense in X if the closure of A is equal to X. That is the whole topological space. So I took the example between Q and R because R is our X in this case, right? So R is equal to X, and now our Q is A. So the closure of Q is equal to R, so it's the second case. But if A and B are both subset of X, the underlying set, then you have inclusion. Like that is, density means that the closure of A contains B. Obviously, the closure of A will be equal to B if B itself is closed. This is correct. This is good to know. Because if A is contained in B, the closure of A is contained in the closure of B. Closure of B being equal to B if and only if B is closed. So if you look at this result here, this theorem, this result, you can see that if B is contained in A, then the closure of B is also contained in the closure of A. But we know that if A is closed, that closure is equal to A. Right. Good. Another definition, nowhere dense. So it's said to be nowhere dense if it is dense in no open set at all. That is, if the interior of its closure is empty. Nowhere dense. A is nowhere dense if the interior of the closure of A is empty. That is, there's no interior, right? Because I say the interior of, that is, it is empty inside. It is empty. Okay, so here we have some examples. Q is dense in R, I mentioned that already. And if we endow R with this usual topology, we take a sequence. You can see S here is a sequence. Right? And now if you take the closure of this sequence, it's still the same. Now, if you take for the usual topology, remember, if you take the interior, because this is not an interval. Now, if you take the interior of that, you see that between two sets like that, I mean, if you take two consecutive points, in between there's nothing. So if you take the closure with the and the interior, you'll see that it will be empty. Because for the topology of R, we know that the interior of something is an open set, right? But since this is discrete, they cannot be interior. You can look at this. Interior of A is denoted this one. And what is interior? They say the interior is the largest open set contained in A. So you see that the interior of a set is an open set. It's the largest open set contained. Because when you say it's interior, it has to be inside. The interior of A has to be inside of A, but it has to be the largest open set. So the interior of a set is an open set because it's the largest open set contained in that set. Okay, and we know that for the topology of R, an open set is an open interval. Now, if you look at this one, you don't have any interval here. You have discrete point. So the interior has to be an open interval. But since they are not, this is not an interval, but they are discrete, there's no interior. The interior is empty. Okay. Now, this is a formalism. We are trying to formalize the usual topology of R using the previous definition. That is, X is a R, and now T, our topology. This is how we define it. We know that an open set, as we already said, that that's neighborhood, right? Because these are, in fact, neighbors, right? Or neighborhood or whatsoever. If you recall what I said a neighbor of a point, or a point is a set is open if and only if it's a neighbor of any of its points. So that's exactly the definition that we are using here to characterize the topology of R. So O will be open. That is O. Remember, topology O, any element of the topology is an open set. Now, what is open set? It has to be a neighborhood of any of its points. So for any X in O, that is the open set for the topology of R. So for any X, I should be able to find something of this form that is contained in O. So something of this form, what is it? This is an open set that contains X, because you see that it's an open. Obviously, this notation, of course, in some textbook, this is the same. So if I say, if you see anywhere here or in some textbook, this is the same as AB, like that. Okay? This is to say open at A and B, right? This is the opposite of closed, because remember when you say something is closed at B, you do this. But if you take the opposite of this, you say open. So you can write open like this or like this. So this is closed. If you transpose, you change, if you flip this definition of closed, it will give you this, which is open. So if you see closed like this, I mean open like this or like that, is the same thing. Okay. Exactly the same thing. The same thing. Okay, so that's how we define the topology of R. Right. So if you say usual topology, this is how the open sets are defined. So for any element in that open set, it contains this open interval. Right? Center, because this is an interval center at A. And what is the radius of that? The radius is epsilon. Right? The radius is epsilon. So from the center to that end, you add epsilon. The center is X, you add epsilon. On the other side, same thing. From here to that other, you add epsilon. Okay. We have other definitions here. Definition of convergence, continuity. In terms of topological spaces, this is how we write convergence. It's not different from what you did in real analysis using intervals, right? So if you use this definition and apply this to the usual topology of R, you see that it will give you exactly what you know, right? So your V here, neighborhood of x0, will be written in this form. And if you rewrite using this definition of neighborhood of x0, so this will be x0 minus epsilon, x0 plus epsilon. So if you write it here, to say that xn is in that neighborhood, right? For R, I would say xn belongs to this neighborhood, that is x0 minus epsilon, comma, x0 plus epsilon, like this. But what is the meaning of this? If I rewrite this, it just means that xn minus x0 is less than epsilon. And that's it. And this is exactly what you know from real analysis, right? That xn will convert to x0 if you have this. If there exists a rank or something, such that for any x greater than that rank, this is true. Right. Now, you also know that this is equivalent to what? That this is in between negative epsilon, epsilon, right? So if you rewrite this, you write it as negative epsilon less than xn minus x0 less than epsilon, right? And this is equivalent to what? Now, if I get xn, so I add x0 on both sides, that will be x0 minus epsilon less than xn less than x0 plus epsilon. So what is this? This is exactly the same as this. So this means that xn is in the interval x0 minus epsilon, x0 plus epsilon. So it's exactly the same. So this is equivalent to this. And that's what you know from the topology of R. Topology of R. Okay. So the concept here just generalized to any arbitrary topology. This is really very important to know. Why do you need to know all this? Because as you will see later on when we'll be talking about Banach spaces or Hilbert spaces or whatsoever, then you'll be able to write the convergence. Once you know general topology, because a topology, as you will see later on, can be defined by a distance, that's matrix space. From a matrix space, you can define a topology. And you should be able to write a converging sequence in that particular topology. Similarly, in an arbitrary Banach space, which will be defined by a norm, where the open sets will be defined, or the balls will be defined by norms and the like. So you mimic exactly what we are doing here. So it's very important to know these things, this elementary topology, because it gives you a broad understanding of what it means to converge. Okay. The next element here is about a separated space or an Hausdorff or a Hausdorff space. A Hausdorff space just means that if you have two discrete points, arbitrary points, if they are distinct, not discrete as I said, if you have 2 points that are distinct, they are different, then you can find the neighborhood of each one of them that are disjoint. So if this is true for a topological space, you say that topological space is Hausdorff, or is a Hausdorff space. R, for instance, is Hausdorff. If you take the usual topology of R for any two different points in R, you can write this. This will be true. In R, if I take, let's say, A, B, two elements of R, I can show that R is separated. It's a separated space, or R is a Hausdorff space. So let me do that. I will do that. I will do that for the topology of R. And after that, I would have liked to define what is the initial topology. I don't know if I will have enough time to cover that. Maybe not. This initial topology is very important, and I want to cover that because we will use this in later on when we'll be talking about weak topology. When we're talking about weak topology, we'll be using this idea of initial topology. Please bear that in mind, initial topology. But let us do this. Obviously, the rest I will not really go into the other. You can read this day. You are mature enough to read these various, because this topic is really vast. So if I have to go there, we will not cover enough. But you have the notes, you can read. Maybe as we proceed, some aspect that I did not mention here, we might come back to that. But so far, so good, I think. What we have done is enough. Okay, now the topology of R, let me quickly share a new slide with you and show that R is Hausdorff. So R indoor with its usual topology is R indoor with its usual topology. That is okay. Endow with its usual topology, usual topology is Hausdorff. That is for any 2 points, x1, x2, or AB. Okay, let us leave x1, x2. Element of R such that x1 is different from x2, right? We can find O1 in the neighborhood of course, this is open in the neighborhood of O. When I write O, it's assumed to be open, right? In the neighborhood of x1 and of course, this existence is for both O1 and O2. I don't have to repeat this existence. In the neighborhood of x2, search, of course, search that already, right? With O1 intersection O2 empty, so they don't have points in common. So in other words, this is exactly what it means. If you want to represent that in R, so I have x1, x2, right? Obviously, they are distinct. If they are distinct, there's a distance between. So I just magnify by doing this. They can be as close as you can imagine, but that distance in between, because they are not the same, they are distinct. So there is a distance between. Regardless, even if it's 1/1 billion, that distance, even 1/1 billion is close to 0. Even if a virus, the smallest virus you can imagine, can be in between there, that distance can be magnified for you to see exactly this. Right, so that is the distance in between. So this is x1. We have x1 here, and we have x2 there. Now, so this is a open neighborhood of A. So you can always, so this is the distance, right? So this, I can call it D, eh? This distance is D. Okay, let me, okay, anyway, let me denote that distance. Okay, so that distance, we call it D, right, that distance. Okay? All right, so this O can be this, 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 this. So this is O1, and this is O2. This is always possible. Now, how do we prove it? So easy. Hmm? Really, really easy. Easy. Okay, so it's really easy. Yeah? You can believe me when I say easy, it's easy. Oh, believe me, guy. Okay, so we know that in R we have that. So I can just, this is the distance, right? So this distance, how do I write it? I can take this distance D is just absolute value x1 minus x2, or x2 minus x1 is exactly the same thing. So this is the distance between the two. So this distance is positive. Why? Because x1 is different from x2. If x1 is different from x2, the distance is positive. It can only be 0 if we know that absolute value is greater than or equal to 0. It will be equal to 0 if x1 is equal to x2. If they are different, strictly positive. Good. Now, because it's strictly positive, right? Now I can take the radius of this, of either of this, to be less than d by 2, because remember that from here to there, to the middle somewhere there, if I take that to be less and the other one also to be less, they will never intersect there. So I can just let my epsilon, because epsilon will be like this radius, right? That distance. Of course, if I decide to stick center interval, center of x, then I will be using epsilon like this. So I used my epsilon, right? Less, I will take it less than d by 2. If my epsilon is less than that distance by 2, and I take d by 2. So let epsilon less than d by 2, I'm done, right? So if that is, I just can construct my O1 open interval to be the interval x1 minus epsilon x1 plus epsilon. And similarly, O2 x2 plus epsilon So for this choice, I'm good. Because why? Can you prove me the contrary? Can you find a point, a point that is common to the two? No, it's impossible. It's impossible if I give you, I will be generous. Because if I say if I give you a billion here, you will never reach that billion here. I will be generous. I'll give you the rest of your life to go and look for the point that is common to the two. You will never find. And I don't need to wait for you to leave until the end of your day. You'll be searching. I will just take a few seconds to prove you that it's not possible. So I claim here that A1 intersection A2 is empty. Okay, you say no. Okay, you say no. You say no. Okay. Now let's suppose that there's a point. Suppose X is an element of the intersection. Right? Okay, so you belong to both, right? If it's there, it means that is just elementary. It is here and it's there. Right. But what does that mean? That is here and it's there. So that means for the first one, right? So if it is there, if it is here, it means that the distance between x1 and x is less than epsilon. That's what it means. And similarly for the other one. So it means that the distance between x and x1 is less than epsilon. And the distance between x and x2 is less than epsilon. That's what it means, right? Good. Oh, one property of R, if you remember. Did I say R? Yes. One property of R, or of the absolute value, we know that, maybe you don't know, but I know that if I take the distance from x1 to x2, right? From x1 to x2, I can say that this distance is less than or equal to, is it the right thing to say? Yes, I think so. But let's see. So what I'm saying is that the distance from x1 to x2 will be less than or equal to the distance from x1 to x plus the distance from x to x2. That is obvious. Obvious. So this will be less than or equal to the distance from x1 to x plus the distance from x to x2. So what am I doing here? To write this is easy. Yeah, I just take x1 minus x2, and I put, and I subtract and I add. I subtract and I add x. You can see that this is this one and this is that one. I can cancel and get the other one, right? So this is the same as that. But I know that absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. That's property of R, absolute value in R. So this is my a and this is my b. So I can split that into two, so I get this. So it's not witchcraft. Anyway, things like this, I don't really need to waste my time writing things that are trivial. You know these things, so there's no waste of time. So this is what we have. Okay, but what is the meaning of this? Oh, this one. We know that this is that one. So this is less than epsilon. The other one is less than epsilon. So the sum of the two, this is strictly less than 2 epsilon. So I can write that this is strictly less than 2 epsilon, right? 2 epsilon. Now, if I look at this one, what is this? What is this distance? x1, x2. That's what I call d here, right? So this is d. So d, which is the distance from x1 to x2, is less than 2 epsilon. But what is 2 epsilon? From here, look at this. Epsilon is less than d by 2. So 2 epsilon is less than d. Do you see something? I hope you are not puzzled. So I'm saying that d is less than d. We started with d here. And we reached to d is less than d. Contradiction, this is impossible. So the assumption is wrong. So x cannot be there. In other words, the intersection is empty. All right. This is really elementary. Yeah? That's just a waste of time or a revision. I don't know what to say. But anyway. Okay, what we have written here is for R and O with this topology. Now, we will define what is a metric space. And in a metric space, we define balls. And we will see that some metric spaces are Hausdorff. Instead of using the interval as we did here, we'll be using balls. And we do exactly the same thing. Right. That is about metric spaces. So we are done with R and O also is Hausdorff. So that's the proof. So you can do the same thing for an arbitrary metric space. Metric space. Instead of using this, you'll be using balls centered at a point of a certain radius. The proof is exactly the same. All right, exactly the same. So I would proceed with the note. Okay, continuity. If you recall what we did when we defined measurable functions. If you recall measurable, what's the measurable function? A measurable mapping. Okay, continuity given two topological spaces, x, y. Now, if you have a function f defined from x to y, where x is endowed with its topology and y with its topology, respectively t sub x, t sub y. The definition of continuity in this case is similar to what we say the function is measurable with respect to the topology. In other words, for any O in the destination topology, destination meaning that where the range is, that's destination because you have the source, the destination. F is defined from x to y. X is the source, y is the destination or the target. Source, target. Target space, source space is x, target space is y. So you take any element in the target space, you take the reciprocal, it has to be in the topology of the source space. So what we did with sigma algebra, we replaced our sigma algebra here with topological spaces. So for any O in the topology, so that's like for any O in the sigma algebra, obviously a topology is not a sigma algebra. I'm just saying that. I'm saying it is similar by similarity. So for any O in Ty, which is the target topology, the pre-image of O is in the source topology. So that is continuity. The way you can see now, you can take x equal to r, y equal to r. The topology there is open sets, right? Open sets. Open set with open intervals. Open interval, you can measure the distance using absolute value. So if you write this for the topology indoor the usual topology of R, it will give you exactly the definition of a continuous function the way you saw in calculus. Yeah, in calculus. Where you say for any epsilon, you see, for any epsilon, we say for any open set there, for any epsilon, because for any open set, we say any epsilon. If you go to the topology of R, this one you can see here, for any O, we'll be talking about things like this. But any O, we'll talk about for any epsilon. Because the topology, the O, the open set, we can take this to be O. For an arbitrary open set, we say for any O. For any O, for any O, for any O. For a given O, we can define that O as an open interval, right? So you'll be able also to see the same thing here. Right. Okay, I leave that. Homomorphism, you can read that. Sequential continuity, you can read that. Okay. Initial topology. Okay, I will say something about initial topology and we'll stop. Initial topology. We'll stop, and tomorrow I will record another one where I will be talking about compactness or compact topological spaces, compact set. They are really useful definitions, compact, because you cannot do this course, cannot take this course without knowing what is a compact set and the implication of that. So, X is a non-empty set, and we take a family of topological spaces, Y sub I, where I is an element of the set of indices, capital I. Now, we define a family of mappings. That is our calligraphic F. It's a family of mapping. So the mappings are defined from X to each of the Y sub I. So you see that family, the index f sub I is in capital I, right? The same cardinality as this I. So the number of y sub I will correspond to the number of y of f sub I. Okay, so that's the family. So we have that family. We have the family of mapping. We know already what it means for a function to be continuous for a topology. Yeah? This is where we define a continuous function, right? So X is a topological space. All the family of Y's, they are all topological spaces. So we can define what it means. If you want this F to be continuous, we know what it means, right? We know what it means, continuity. Okay, so now we are told that we can define a topology on X that makes every F sub I continuous. We can define a topology on X that will make each of these mapping continuous. And that topology will be the initial topology. I can already say it here. Okay, so the weakest, of course, when we talk about the weakest, because the trivial, as you can see here, but not the trivial, the discrete one, yeah, which is trivial, discrete trivial. Is it a trivial? The discrete topology. No, the discrete topology is not the trivial. The discrete topology is the power set, if you recall, the power set. Power set. That is the discrete. The trivial is just the topology consisting of two sets, the empty set and the underlying set. Let's say X. We are defining topology on X. So that is the trivial. The discrete is the power set. Px, Pyi, and so that one, that topology, the discrete topology, obviously will make this mapping continuous, obviously. But we don't want the discrete topology. We want a cross-set topology, that is a topology smaller than the power set, right? Okay. There might be many, but the weakest or the closest or the smallest topology will be the one that we will keep, right? And it's like a topology generated. That's the smallest. So that's why we call it sigma xf. So the weakest or the closest topology on X that makes every f sub I continuous is called the initial topology, and it's denoted sigma xf. That is the smallest topology. Or if we can say generated by or something, but that's not exactly the idea. But that is it. That is the smallest topology that makes this family of mapping continuous is called the initial topology. And that's exactly the same topology we'll be using later on when we'll be talking about weak convergence, weak topology. So when we're talking about weak topology, because you can see here it's a weakest. So later on when we're talking about the weak topology of a Banach space, we'll be relating to, we'll be referring to this initial topology. Example, if we take X and Y to be R, and we define this function f, which is negative for x less than 0 and 1 for x positive. Obviously, we equip y with the usual topology. That is usual topology of R. Now, we want to define a new topology on X that will make this function f continuous, right? That will be the initial topology. So that initial topology will be given by this. So the open sets for that topology will be the empty set, the interval open at infinity, close at 1, the interval from 0 to infinity, the open interval from 0 to infinity, and R itself, because topology, you see, topology has to contain the empty set and R in those. Okay, so this will be that initial topology. It will be defined by these 1, 2, 3, 4 open sets. And you can verify that indeed this is a topology in the sense of the definition of the topology. So this is a topology. Okay, so we'll stop here for today. And we will continue next time with the same. But I really encourage you to read this part. Please read it. And prepare for compactness, because tomorrow I will tackle compactness. Is there any need to proceed and say something? Okay, let me take a few minutes again to quickly say something here. A collection B of open sets is called a base for the topological space if and only if any open set of the topology can be written as an arbitrary union of elements of the basis. That's the definition. So I'm given a topological spaces. I want to find a basis for that topological space. Or I'm a given a collection of open sets. I'm asked to show that that collection of open set is a basis, or a base is a base of for the topological spaces. So how the topological space. So how am I going to do that? I'll just take an arbitrary element of the topology and show that. I will take an arbitrary open set of that topology and show that it can be written as an arbitrary union of element of the basis. So if I do that, I'm done. So that's just the definition. You don't prove the definition. Okay. Now we have the following proposition. A collection of open sets B is a base for the topological spaces, the topological space XT, if and only if for any O in the topological space or in the topology, and any X in O, we can find an element of the base containing X and contained in O. So this one now you can prove it. It's if and only if. So we have to prove in both directions. Second proposition is about initial topology and sequences that we are going to characterize convergence. Let X be a set and Y sub I a family of topological spaces. So X here is a set. It's not a topological spaces, but the Y sub I's are topological spaces. So now we have another family here of mapping. Family of mappings, so F sub I defined from X to Y sub I. And now we have a sequence of element of X sub N. We define the initial topology on X. Sigma X with a collection of S sub I. Now, that sequence will converge in X. The sequence Xn will converge in X, endowed with the initial topology, if and only if the image of Xn by all the f sub I will converge to the image of X0 in in Y sub I for any I. So this is what we call sequential convergence, right? Sequential convergence. Because if you take the initial topology, all these functions f sub I are continuous. That's what the initial topology means, right? So now you are told that if all these images, that is for each sub I, the image of Xn by f sub I will converge to f sub I of X0, right? Then, in fact, it's an equivalence, right? If that is true, it means that Xn will converge to X0 for the initial topology. And if X converges to if Xn converges to X0 for the initial topology, it also implies that all the images by f sub I of Xn will converge to fi of X0. So if you go to the definition of sequential convergence, you understand exactly what I'm talking about. I mean, sequential continuity. Sequential continuity is exactly characterized by that. This is sequential continuity. The function is continuous if that is true. But because the f sub I are already continuous for the initial topology, obviously, this can be used to characterize a converging sequence in the initial or for the initial topology. So this proposition, in fact, characterizes the convergence sequence for the for the initial topology. And this is exactly the same convergence we'll be using later on when we'll be talking about weak topology in a Banach space. We have a Banach space which already has its norm, and now we have the strong topology defined by the norm, but we can also define the weak topology by constructing initial topology. We will see that later on. All right, and finally, the final result is this lemma. This lemma, I will not even speak, because the proof for this proposition relies on this lemma, so I will not state it, right? Because I'm not going to prove the proposition. Okay, dear student, thank you for your patience, because as you'll be watching the video, you need to be patient, right? So what I covered here, I wish you all the best in the reading, in solving the problems. So I will stop here for today. If you have any concern, please send me an email and let me know so that we see how to address the problem. So if there's no further question, I think I will stop here. I wish you all the best. God bless you and see you next time. Bye-bye. And enjoy, 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 enjoy.